we partner with Google, and we can help you through the journey if you'd like to get involved with Google. They've got superior products. A lot of the team from Great Data Minds was Google Partner of the Year a few years back, and I have to tell you, the work we were doing with the platform was just amazing. With very large organizations, we were cranking stuff out. So excited to have you guys going. I'm going to turn it over, and let's get that chatter going over in the chat box.
Yeah, thank you so much, Julie. And yeah, appreciate the opportunity with the Technology Matters Conference, a slot here to talk a little bit about some of our tech, our favorite topic. And so just to kind of give you some guidance on how we split up the hour that we're going to spend, or almost hour, you know, in the spirit of speed dating, I know you're all getting different perspectives from different partners. And so Mark and I decided that there were kind of two topics, all under the umbrella of AI and ML at Google Cloud, that we wanted to hit on. So first, as an introduction, my name is Anil Roney. I'm a customer engineer, not necessarily focused on AI and ML, but actually more data engineering, right? Data warehousing, BI, reporting. And so I'm gonna spend the first few minutes actually showcasing AutoML. It's a service available on Google Cloud that is very beneficial to me as a data analyst, data engineer, at best citizen data scientist, to actually help my customers start getting predictive solutions without necessarily being a data scientist. So that'll be the first few minutes. And then secondly, I'm going to hand over to Mark to bring more of a data science practitioner perspective and just really talk a little bit about how we're seeing scientific ML weave its way into how we're solving some of the real tricky and hard problems in and around ML for our customers. So with that being said, we'll have some contact information. We're gonna, if we do this right, we're gonna have some great Q&A at the end of this session, but certainly feel free to reach out to Mark or myself from the Google team. So as mentioned, I'm gonna dive right into AutoML and talk a little bit about where I see this service being utilized at customers, what it might look like. I'll do a very high level demo to showcase essentially what ML looks like in a no-code framework. So with that, whoops, let me go the right way. Let me just orient out of the gate. So when we talk about building machine learning and AI solutions on Google Cloud, there are many, many, many different services and options. But just as a first orientation, I'll start with the right-hand side of this slide, and you can see these sort of three pillars we think about when we're presented with an AI and ML problem, sort of shuffling it into one of these pillars. So on the right-hand side, I like to describe these as AI or ML problems that have already been solved, right? So we've used our Google data to train these models. They are our models. We think they're very accurate. They do a great job. And so, for example, like if you're needing to do some translation, right? That's a problem that Google Translate solved a long time ago. You can actually, if you need translation within your application or the solution that you're building out, you would just call our translation API, lots of different languages to and from that we can deal with there. Same thing with some of our like cloud vision, right? Detecting typical objects in images or even video. You know, humans in a photograph, or humans, right? You could think about what we do with Google Photos. We've solved that problem quite a while ago. And so if you have need for some typical object detection, we can do that using our Cloud Vision API. So the right-hand side is really like the problem's been solved, but I need a way to integrate it into my application. I'll jump over on the left-hand side. This is the heavy lifting services, right? If your business, your organization's solving a very niche industry custom problem to your business that involves ML or predictive capabilities, right? You may need things like heavy duty compute, GPUs, TPUs. You may need a container orchestrator to actually deploy these models, potentially maybe out to the edge at a manufacturing facility or something like that. You may need some elements of big data compute, right? Spark or something like that. We have that available on our Cloud Data Proc service, which is a managed Hadoop implementation. And then just in general, being able to serve out models that your data science team builds out. So that's the left-hand side, a lot of great heavy lifting services for that custom ML development. And what I'm going to touch on today is AutoML, right in the middle, right? A little bit different, actually utilizing our models, right? And all the benefits of Google Brain, right? Our internal R&D and model and algorithm library of all the different problems we've solved, but really fine tuning and training those models on your actual data. And just to make a statement, AutoML has a lot of different flavors. You can use AutoML for vision, translate, natural language processing. But I'm going to talk about AutoML tables today. And I'll talk why I think I'm seeing that more and more with customers. But really, that's about leveraging AutoML, which another way to define that is a model that can traverse other models to figure out the right model that's appropriate for your data, right? So I'll talk a little bit more about that, but your data can be sitting in a relational data warehouse, an Excel file, a CSV file, a Google Sheet, etc. So I'm going to talk more about that here in a moment. So to oversimplify this, right? And again, I'm putting on my citizen data scientist hat. If we oversimplify sort of the ML experimentation process, what our goal of AutoML is from a Google perspective is you bring your data in a data set. And again, I'm going to talk about structured data in tables. You hand it to AutoML, which is actually going to do the heavy lifting of inspecting that data, training. It's going to take care of deployment in terms of a REST API endpoint. But essentially, after you hand it to AutoML, it's giving you a model back and all the statistical information you would want about, is this an accurate model? Did Google do a good job? And can I actually use this within my business? So that's sort of the rough framework and guidance that we think about from the AutoML service. I've already mentioned we have a few different flavors of this, probably going back a couple years now, where we had AutoML for vision, video, natural language, and translation. However, about a year ago, we recognized a real importance to be able to use the AutoML paradigm on actual table data or structured data. So I think we're all familiar with structured data, but just to level set here, right? Like, again, if you think about your data warehouse, your relational databases, dumping data out into CSV files. In this example, right, you might have a history of some transactions or prices for these particular products. In this case, it looks like different shoes, right? And the key thing with structured data is if I have like all of this information, right, the transaction, what type of shoe it was, what category or brand it was, and I wanted to predict future prices being sold, or what, you know, if I'm working through like a dynamic pricing mechanism, I want to look at historical transactions and say, for this particular product, what price can I predict might be sold? And that's really where AutoML tables come in. You have this data and you're just coming to the table with the question of, can I predict what these products are going to sell for in a future transaction? As just one example of AutoML. This touches on what I mentioned. If you think about like, look, Google AI, you know, doing really cool things with images, video, text, like audio, super cool stuff. And we have great capabilities there. But the reality is what we see is the typical predictive or forecasting type problems that we're asked to solve on behalf of our customers fall in those top two categories. So when we think about forecasting, often it's historical time series data, financial transactions, et cetera. But really a lot of the problems boil down to, I have this data, whether it's about my customer, about my business, different lines of business, and I have it in some structured format. I want to leverage ML to do some prediction. So AutoML tables has a wide variety of applications. And I'm going to just click through a demo here real quick to show you, again, as a citizen data scientist, how can I build an ML model with zero code using AutoML tables based on data that might be sitting in my data warehouse. But as I go through this demo, it's not going to be a real deep dive or a specific use case, right? My goal here is to click you through the mechanics, but I'm hoping as you're listening, you're thinking through whether it's your specific industry or your internal customers you support in finance or marketing, right? These different type of predictive themes that you're hearing, and hopefully through AutoML tables map it to, I might be able to take a shot at that, right? Let me get a baseline model and see if it's something that could be valuable to my business. So with that, I'm going to show you AutoML tables and really just the mechanics of how this works. And it is a no-code solution, right? So normally I would jump off and I'd go in the Google Cloud Console, but I'm just going to take you through exactly the steps to leverage AutoML on your tabular data. So here we're in the Google Cloud Platform Console. We're within the AI platform, and you can see it's just a very basic menu of choices when you're thinking about solving an ML problem, right? Preparing your training data, training your model, and then ultimately getting some predictions. So the first step is I need to bring some data to the table, right? So I'm going to walk through creating a data set. And here you can see in the middle there across, like, what is your objective? What kind of data are we dealing with? Image, text, translation, video. In this case, we're dealing with tabular data. And you'll see I just have some sample data in a CSV file here in a moment, and then some guidance on like what type of problem are you trying to solve, or what is your objective? Is it regression or classification, or more classic time series forecasting? I basically say what region on Google Cloud I want to host this AutoML model, and then I actually import data, right? And so a couple options here. More times than not, I'm working with customers who have integrated a whole bunch of data in BigQuery, which is our data warehousing analytics platform on Google Cloud. But you could just bring data from other sources, lay it down on Google Cloud Storage as a CSV or Avro file, something like that. Or in a very basic experiment, just upload that data from your computer. And you're going to give AutoML a location. Where are you going to store the data in Google Cloud Storage? So now I've brought my data. It's going to walk through processing that data set, importing it, and then it's going to start giving you back some information about that schema and some statistics that may be interesting, right? So here, in this case, just a very simplistic example, I have some demographic information, essentially about some retail banking transactions, and sort of the ultimate goal would be, can I predict the amount of the next deposit based on some customer demographics like age, what their current balance is, any campaigns that I've run to market to those customers, et cetera. And so you see, I'm going to get some baseline statistical information. As we know, garbage in, garbage out. So like if I've chosen some features in my data set that have a bunch of missing values, that might be an issue. AutoML doesn't do any magic for dirty data, right? You're going to have some semblance of, this is the right type of data I would want to bring in as features to actually make a prediction. So it'll give you baseline statistics. It'll allow you to look at those statistics. And then ultimately, I'm going to say, I want to build a model. And I'm going to give it very basic information. What is my target column? What is my label? What is it that I want to predict? And actually, in this example, we want to predict that deposit amount based on age, campaign run, et cetera, right? So I'm telling it, I want to predict deposit. My objective is tabular classification, and you see some options here. Again, when I'm using AutoML tables, I'm using the default, like automatically split my data between training and testing, but you can be more granular if you would like to. I touched on this, and then here's the training budget. So here's where your cost actually comes in, which is important. Essentially, what you're saying here is, how long do I want to ask Google AutoML to crank on this problem? And again, when I say crank on this problem, it's our AutoML model going out and saying, based on the data you're feeding me, let me iterate through all the models I know about in the Google library, look at features, look at different accuracies coming out of that model so that I can hand you back the best model. The more time you give it, in theory, right, the more accurate your model can become. One thing you'll see in this is early stopping. So cool safety net would be, if I'm asking AutoML to crank on this for 8 hours of compute time over AutoML, and at 4 hours, AutoML is smart enough to recognize there's diminishing returns to actually continue cranking, and it'll stop that and save you some money. But here you can go from as granular as just go look at this problem for an hour and give me the best model back, or go look at it for 100 hours. And that's where your cost comes in. So once AutoML comes back, I gave it an 8-hour parameter there. It comes back, it's going to give you a model. Here's the best model we think we fit to the data and the label that you're trying to predict for. This is where typically I bring Mark in, right, to sit with me and say, am I getting the right statistical accuracy, right? Area under the curve, precision and recall. So that's all available to you to look at and analyze within the Google Cloud Console to see if you've actually gotten a model that would benefit your business. Confusion matrix, right? How the model performed on the test data. And then certain other statistical elements like what features were actually driving the accuracy of that model. So maybe you need to pare down the model, maybe you need to bring in additional columns that could better predict that deposit value in this case. And then the last thing is, let's just assume I got to a good model, and that model was pretty good in terms of accuracy and predicting the deposit amount. The next hard thing in the world of data science, as many of you know, is how do I actually deploy that model? So from AutoML, once you're happy with the model that's given back, let's say I say, this is doing a really good job predicting the amount of deposits that are going to come from my retail banking customers. I can simply just deploy it here within Google to an endpoint and take that REST API endpoint and then hand off to my developers to say, if you can include this into our mobile application or whatever application, they simply can plug and play. And you can also test it here right within the interface. So I can actually input some of my input values, and it'll use the model to make that prediction if I want to do some very onesie twosie type testing against the model. So with that, here's some model settings for deployment, right? There's some compute resource considerations, like, again, how many calls to this model am I going to make? I'm going to want to scale. Very easy, again, just through the interface. And then you can ultimately deploy it, like I mentioned. One other option besides the REST endpoint that I didn't cover is also if you're looking at taking this model and pushing it out to an edge. For example, I work with customers who have manufacturing facilities, low bandwidth, right? They want to take a quality prediction model for their manufacturing process and actually push it to an end device that's actually sitting right there in the plant. We have that option to deploy via Kubernetes and containers in that instance as well. So with that, I know that was super fast, but hopefully I gave you a quick overview of, again, bring your data, leverage AutoML. One thing I didn't know, and if you're a data scientist on the call, you're probably thinking, that's too simple, right? And you're right. One thing I would call out is a lot of times when I'm working with practitioners like Mark, for example, AutoML is a tool they often use just to baseline, right? If your data is already sitting in your data warehouse and you know you want to predict deposits, AutoML is a quick and cost-effective way to really get that baseline. Now, your problem may be a little bit more complex, and maybe that model could be shared with your data science team to further iterate or maybe customize that model. So while I use it to get a quick prediction, like inside of my data warehouse data, which is a very, very typical use case, and I don't need to be a data scientist, a lot of times I work with customers where their data scientist team use AutoML as one piece of sort of the overarching machine learning lifecycle. So with that, I'll stop there and I will go ahead and hand off. And Mark, we can transition to scientific ML. And I can't see the screen, but keep the questions coming and we're going to leave some time at the end for those.
Hey, Anil, I had a private chat come through. Yeah. While you guys are transitioning, can you give us a high-level update on their differentiators as opposed to Microsoft and AWS?
Yeah, so you're going to see AutoML services. As a side note, I worked on Azure for many years. I've done implementation on AWS. I think the key differentiator, and I don't have a slide to bring it out, but I would look at the number of algorithms underneath the hood of our AutoML service, again, from Google Brain. So one statistic that's very interesting to share is, like, if you look at, if you're familiar with like Kaggle competitions, right, where ML or AI problems are thrown out there for a community to go solve, we've actually leveraged AutoML, and we're in like the top 7% across all Kaggle competitions utilizing AutoML. So I would say the libraries underneath the hood that we're able to iterate through to come up with that model that AutoML is handing out is vast, number one. And then at the end of the day, there are other services, right, that can do this framework of bring your data, give me a model to make a prediction. Obviously, all that comes down to accuracy, right? And so that would be one area that I would look at as I'm comparing different AutoML services.
Okay. And Neil, this is Mike. How often are libraries and algorithms being deposited? Are you guys continually enriching it?
Yeah, I mean the the quick answer is definitely continual. I honestly don't know the actual sprint pattern for that.
Okay.
But again, you can imagine from a Google perspective, being very agile, we are continuing to fine tune. And again, there's machine learning under the hood. So it's continually learning as customers use the example, what models are producing the best accuracy. But in terms of adding algorithms, it's a regular cadence. I don't know what the exact cadence is.
Cool. Thank you, sir.
And yeah, there's regular, what we didn't do before this is look at what we could share, but there are definitely queued up AutoML components that are ready to be released and on a schedule. There's more about structured data, and then there's more about kind of enabling you to do more search type things and explore variations on your own. So, okay, I grabbed the screen, Anil. I'm sorry, what was that?
I was just offering a little color. It's exciting times.
Oh, yeah. Well, we'll get there.
Mark, you're welcome to grab the screen.
I think I did, right? This is me. Everybody seeing this? That change?
Yes, we are.
Yeah, you're good.
Okay, great. Cool. So, hi, I'm Mark. I'm a solutions architect with Google Cloud. I have two specialties. One is data engineering. I teach a data engineering class in Berkeley's Data Science Online Master's program. It's really a class about just enough data engineering for the data scientists to be effective in the rest of the program, as well as to be effective in their jobs later. There's a real trend, and we'll talk about that in a second, to bring your own engineering into this. I have another specialty, and that's I have a doctorate in physics. I help customers with more scientific machine learning problems and ways in which we can apply AI ML techniques to solve what would be traditionally sort of old school science problems. So I'd like to share, I'm going to take this in a little different direction here instead of talking to you about our product line and things like this. And we can answer questions on all that, and we can cut to that at the end. I'd like to share some of, and actually ask you for some things as part of the data science community. I think there's a lot of really, like, you know, you mentioned, it is very exciting times. We're in the midst of an absolute revolution in how we solve problems and use some of these tools. And it's one of my thrills to be able to share this with you and share this with the community. So before we get into that, I'd like to go over a little bit more of, and I talked about this last time. I'm not going to talk a whole lot about ML ops here and operationalizing ML. At this point, that's sort of old news. You know that train's left the station really, and you hopefully have been looking over the past couple of years at ways in which you can help, you know, ways in which vendors are providing tools that help you operationalize your machine learning algorithm and you know, model development and model training and model evaluation processes. They don't look like they did a few years ago, and we could talk for hours about the set of, you know, the way all the different vendors are providing tools that help us do this now. In the, you know, the short story is that, you know, it's easy to kick around models in notebooks, but to put that in actual production is hard. And production doesn't just mean scale. Production means reliability as well. And that's kind of the trick here is, and again, I said before, data scientists are expected to bring their own engineering nowadays and their own engineering chops. So recognizing and learning about the tools that are available, where those tools would be used in particular data pipelines, and how those data pipelines are formed in order to create and in order to serve the models you build or help you develop the models themselves or test the models that you're working on. That's a critical component to being a data scientist these days. And the net result of ML ops there is that we've stolen a lot of really great ideas from the site reliability engineering community, the DevOps community, if you will, hence the ML ops name on there. So infrastructure as code. Infrastructure as code has a lot of immediate ramifications where you start using like a GitOps process. You start automation is part of adopting infrastructure as code. And that is really important to building MLOps pipelines, especially in a situation where nowadays you're doing more continuous training. And when you're doing online training like that, you need to be able to automate the pipelines that are needed to provide that training, to get the data plumbed to the right place for the models to be built and evaluated and validated too. Excuse me. So testing, that leads us to CI/CD pipelines for model development, and the notion of testing our models and maybe dealing with test-driven model development. These are all sort of adopted right now at this point. And the tooling for that is lagging a little, but the tooling for that is something that you should be expecting as a community. I would be demanding in my vendors effectively. Observability is another key aspect of this. Can you instrument, and it's not just the models themselves. Can you instrument the models, but can you instrument the pipelines in such a way that you can determine the validity of your models? A lot of times you just don't know. Reproducibility of a model's evaluation is pretty critical to results, and that's so observability and instrumentation is part of that. Another part here is what I call pipeline prepping, and it's kind of embracing failure as a first-class citizen. And that is sort of, planning for the failure, as much failure as you can, and planning for ways to deal with that. And this becomes, this was, once upon a time, this wasn't that big of a deal. It was sort of an academic interest, if you will. But nowadays we're driving cars, right? So you really have to, there has to be guardrails on top of what we're doing. And we have to just to not only plan for failure, but plan for graceful recovery from failure. And that's, a really key important part of MLOps that we all as a community need to pay more attention to. And we are, but that's, it can't get enough, that message can't be stressed firmly enough, let's say. So I'd like to talk a little bit more about that failure method. Your models, your data pipelines can fail in a number of ways. They can fail in that, data sources got cut off. You got bad connectivity. You got your evaluation engine didn't get deployed in the right way or something like that, right? There are all sorts of ways in which a data pipeline proper can fail. But that's not really what I want to talk about. What I'd like to talk about a little bit is what are the failure modes for your model itself, right? And what does that mean, right? How can your model be bad? And think through that for a second, right? When you create a model, you've gotten data that you've trained it on. You're then making predictions or something based on this model. And that can go, how can that go wrong? One of the most common ways that goes wrong is based on bad data, right? And I say that like, there are flaws associated with collecting the data, and that, you can improve this situation. And there are, and you can, right? And so for instance, an example of this might be that I capture data that represents, I have a sampling bias kind of a thing, right? I've captured data that has a limited distribution across a demographic or something like that. And then I'm going to take those results and I'm going to take that model and I'm going to apply that model to a full population, naively. People do it all the time. And I guess that's probably the biggest problem we've had with modeling in machine learning in general, I think, is that people will take models and will apply them in situations that they're just not, they just weren't trained to, they weren't developed in that context, and they're used out of context. And so I'd rather, instead of talking about the failure of the model, I'd like to talk about the support of the model. Where is the model, instead of saying, where does it fail? Let's say, well, where does it actually even succeed? And let's characterize the range of input parameters for which my model is valid. A really obvious, example of this is you look at time series predictions, right? Well, my model's probably pretty good for data that I've already seen, and probably pretty bad if I'm trying to continue that parameter time, that pesky little parameter, into the future. That's a huge problem in which people are always horribly applying a model outside of its support, outside of its range of validity. So when you as a data scientist, you're developing a model, it's very important for you to recognize when this model is valid based upon the set of input parameters that you're dealing with. A famous example of this from physics, if you will, is springs, right? Hooke, back in the day, did a bunch of experiments and took data on springs, right? We said, oh, well, a spring, you push a spring and it pushes back. You pull a spring and it pulls back. And that trend is kind of linear. You know, he took a bunch of data points and you know, built a model based on this and came up with a linear model. The force is linearly related to the displacement of the spring. Well, that's great for a certain range of parameters, but you go apply this to all the different springs out in the world, and there are elastic limits beyond which the model just fails horribly. That's the example. Everybody has that that's a visceral example for most folks, but what I'd like to point out is that in a lot of machine learning models, we have the exact same kind of limitation. We just have no clue about it. Like we don't have an intuition about it. If we do have an intuition about it, it's usually wrong. The key there is that it's very important to understand the limitations of the models you're developing and the support, the range of parameters for which that model is valid. And if there's one thing I'd like you to take away from this whole talk, is it's this, you need to demand from your vendors, how do I represent the validity of my model? Right? In your tool, you've got a tool for model management. It helps me do all kinds of cool stuff and map it to the training data sets and all kinds of things. So I have my lineage in place and stuff like this. But how do I capture, characterize, and communicate the limited support of my model, and communicate most importantly, right? Because other people are going to consume my model, and they need to understand that, you know, that's a huge part of the conversation that's often lost when you're handing off a model from one person to another, it's not valid in that range that you really want to use it in. So we really need to have a conversation about that. Anyway, so demand that from your vendors, please, to provide the tools, to provide the metadata capabilities associated with that I can attach to a model that characterize the range of validity for that model. And we note that how do you determine this, right? In general, it's kind of a test-driven process, right? You put a set of frameworks in place where you can measure. You have an input, you have outputs, ranges, and you talk about you have a test that you can run, evaluate that model in this test context that allows you to determine and measure and capture what that actual validity is. So it's important to recognize that this is almost like a test-driven model development concept here, is that you're gonna, you know, the activity of, I'm gonna go out, I have this model, I'm gonna go out and actually understand what its limitations are, involves this notion of tests. Okay, so one thing that I'd like to deal with, if we do have such a test harness, this enables an incredible freedom. I'm not sure how many people involved are software developers, but the reason why test-driven development is popular in the software world, or took off in the software world, is because when you have full coverage, you have a good test harness. You have well-defined outputs, well-defined inputs in your software in the other example, in your model in this case, and I can measure when it's wrong. If I can do that, and I have good coverage, I can measure the various different ways that it's wrong. I've got full range of my parameters, and really maybe, you know, catching black swans and things like that. Maybe I can write tests for some of those as well. But the more coverage I have, the more confidence I have that when I make a change to that model or change that code in that example, then I know that the change I make, I'll know when it's wrong, and I'll know when it's right, and I'll know a direction that I can take is good there, right? We of course can make that a little more rigorous with preserving differentiability in our models and handling the way in which we might change some of the models we deal with, and having that reflected directly in the tests we're dealing with. But it's important to recognize that a test harness and test coverage for model development gives us the ability to experiment. So what kind of experimentation do we want to do? And this gets a little more to the point of what I want to cover for the rest of the talk. We talked a second ago about Hooke's law, right? It's some algebraic expression of input parameters and output parameters that I can manipulate with cute little formulas that we all learn in school. Analytical models are great. Closed form models, they're gold, right? It's the holy grail. You'd love to have a good model that's easy to manipulate in closed form that gives you good predictions about a particular system that you're looking at. We, of course, don't usually have analytical models, but it's a class of model that we would swap out in here, right? And so as we swap out the various models, so one thing I might want to do with an closed form analytical model is I might do a linearized approximation. I might do numerical approximations, all of which, of course, can fail in different ways. The linearized model might not be as good at getting a realistic result. The numerical approximation, you might do rounding errors and things like this, truncation errors and stuff, right? So you know, we're able to work with these. We still want to test whether we're wrong, of course. We can't just adopt them naively. But there are other kinds of models. So analytical, linearized analytical models, numerical models that we can put in directly, stochastic models, right? We can deal with non-deterministic things that we use, ways in which we model the world around us. We can use stochastic models for that. And we can also use deep models. You know, highly parameterized arbitrary function approximation, a neural network, is a valid model variation. Now, we can't naively swap these out without this test front harness. Please, you know, that's very, very important. But it gives us the power to be able to swap in all these different variations of things that we traditionally do with an analytical model or a numerical model or a stochastic model. And we'd be able to, we can also add neural networks to that list of tools in our quiver, you know, or arrows in our quiver. As an aside real quick, people talk about explainability, and this is not a Google position, by the way. Google is very interested in explainability for deep models and in trying to establish that. I personally think it's not all that useful. I think explainability because look at the other models you've used. Can you really explain your stochastic models? Can you really explain even your analytical models in a lot of cases? It's familiarity, right? We get used to things. Quantum mechanics is based on stochastic modeling and no one understands it famously, right? So it's one of those things where I don't think explainability is the key to a lot of effective use of AI. I think putting this test framework in place and getting reproducibility and asking, you know, being able to determine the support of a model, being able to determine the validity of a model, and then being able to reproduce results is way more important than being able to explain it. Personal opinion, but okay. So next, what I'd like to do is let's look around us at the world. There are unsung heroes in every aspect of our life. We live in structures, we drive over bridges, we eat food that's processed sometimes in various different ways or purified in various different ways. We drink clean water, we use medicine, you know, that works, effective medications, right? These are all due to various different kinds of engineers directly that are doing the modeling and simulation process and that are doing it very equivalent to a lot of what data scientists do. They're just using, probably more often, they're using analytical models, maybe some linearized approximations of those. And then they are putting those in you know, application for us in our everyday life. And we would not have the kind of quality of life we have without all of those engineers, structural engineers, civil engineers, chemical engineers, biomedical engineers, who else? I'm forgetting all kinds, there's tons of them, right? They should be wearing capes. You should go give an engineer a hug. Maybe wait till after the pandemic, but you know, give them a virtual hug. Any engineers that you know, because they really contribute to the quality of our life, and they are unsung heroes in our current, you know, in popular culture. So I claim that they're working on problems that are in a very similar set of pipelines, in a very similar sort of ways of taking measurements, right? Performing experiments is all about, you know, measuring data, drawing conclusions about the system based upon that data, and then using those models that you're building to predict the outcome. The scientific process is very much intact, and it's very much consistent with data science. So it's a similar sort of thing to what we're dealing with. Their problems are hard because they just at scale sometimes. Global climate modeling can be really hard and expensive. They might be really hard from a complexity standpoint, the complexity of the particular problem they're trying to solve, how electromagnetic waves propagate in a building context or for a car to be able to sense the world around it and make sense of the data that's coming back from that. Those propagation models are really complicated. Not necessarily heavy scale, but really complex. There are also, a lot of what we're dealing with is that, it's very expensive to get better results. You can get some coarse-grained results pretty cheaply, but if you want to get better results, you've got to spend a lot more money and do a lot more, take into account a lot more computing power. So the question is as data scientists, can we help with this? And the answer is yes, and it's awesome, and it's an incredible revolution that we're undergoing. So Jeff Dean, the director of research at Google, is famously quoted on this as it's a deep revolution, pun intended, and he's referring to the chip design industry. But that's the same techniques we're using there, and that's what I'll discuss the rest of this talk. The same classes of techniques we use apply to across the board to a number of these different scientific areas. And at the end of the day, they will matter in our everyday life, from material science to food science to medical science to whatever. Let's talk about the ways in which we can help that situation as data scientists. Let's look at that. So the first class of models I'd like to discuss are surrogate models. And this is where we say, okay, well, physics, go away. You've used these really nice analytical, careful models that you built over the years. They're kind of limited and lame, so let's replace them. Totally take it out with a deep neural net. Boom. So the example here we're looking at, it's not the engineer in the cape, it's the cape itself. So on the left-hand side, the cape is rendered with a very careful fabric model that's very detailed and very physical. It's a physical-based model. On the right-hand side is a neural network approximation. And the key event here is, notice on the left-hand side, it's struggling to render at 2 frames a second. On the right-hand side, I've got many orders of magnitude more than that. So I can run those simulations a lot faster using a surrogate model. Even though it's approximate, it's not a perfect rendition of the cape, but it's roughly there. And there are so many problems that are good enough. And back up to what we were saying before, if you have a testing framework in place to where you know how bad it is, you then decide what's an acceptable level of failure in that. What's an acceptable level of that model not doing as good of a job at the careful fabric rendering on the left. But looking at this, for a lot of purposes, it's not getting the curves in there. It's not getting exactly the same, but it's good. But because of the speed, I can do things, and this is particularly relevant to the chip design that we were talking about before. Because of the speed of a surrogate model in this case, even though I just want an approximation, I can then use that to solve problems I just couldn't even think of solving before computationally. They were computationally intractable in the past. I love this little dance party. So the engineers are enjoying themselves as well they should, and get the accolades they deserve. All right, so that's one class of problems, is where we're dealing with a surrogate, where we just take out the model, take out the classical high performance compute physics model altogether with a deep neural net. There are dangers of that, of course. It's a trade-off, and we can go into that in questions. So inverse problems is the next thing I'd like to talk about. If we have a forward problem, like we have some representation of this molecule that I can do, if I do a normal sort of molecular dynamics model, it's very, very slow. But I can do a neural network model that's, again, many orders of magnitude, in this case, 5 orders of magnitude faster to evaluate, to determine properties of that model. Is it toxic? Does it bind with a given protein, et cetera, right? This kind of analysis is very, very much in use for virus, vaccination development early on in the days of COVID. I was actually on a panel that was helping review proposals for that, and it was really interesting to see some of the ways in which people were using AI to solve what were traditionally some very, very difficult molecular dynamics systems. Anyway, this example is still a forward problem, right? I have the physics, I have the model that I'm dealing with. I have input parameters of various different types, and I get a result out that might be in this case, they're somewhat heuristic models, but there are often times where I don't know the parameters up front, and I want to get what the qualitative result is out the back. I want to say, give me the parameter settings that are going to obtain the qualitative results that I want. So that's basically an inverse problem. And that is really hard to do in physics, and it's really hard to do in general. Partial differential equations that describe a lot of systems that we're dealing with are just really hard to invert. But because it's so fast to do this forward problem, we can effectively invert the problem. And that's so useful. We haven't scratched the surface of what's possible with using deep surrogates to invert problems that we've never been able to invert before. Huge, huge potential. All right, next class of models. We have 5 minutes, it looks like, and I should be spot on with time with that.
Yep.
The next class of models we're dealing with is sort of like using deep models in particular to frame and drive classical high performance compute models, right? To drive the physics. So we have a physics model in the middle that's expensive to compute, right? And we have a set of input parameters and a set of outputs. And oftentimes what you're doing is you're trying to run this, especially, and again, I've been doing a lot of chip design work lately, so I've got a lot of examples from chip design. But a lot of times what you're doing is a global optimization problem where you're running parameter sweeps of the input parameters. And it's just so expensive to run every one of those as, here's my set of inputs, run a simulation for days, weeks, and then get the outputs. And then change those parameters a little bit, parameter sweep, right? And do the same, and it's just horrible. And a lot of these are, chasing I won't talk about derivatives of this, but you of course can use that to help your optimization problems. But what we do in these cases is a lot of times it's intractable to deal with the full parameter sweeps. So we take Monte Carlo type approaches to sampling uniform distributions of the input parameters and then running or sort of sampling various distributions, let's say, of the input parameters to explore the parameter space in some of these optimization problems. That's one where we're using a stochastic approach to drive and reduce the full parameter space that we have to use to solve the particular problem. So we're reducing the overall amount of computation that we have to do to a more tenable amount. Well, maybe a better way to do that is to use a neural network to shape your exploration of parameter space and crawl that a little better than Nelder-Mead blobs or more Monte Carlo sweeps. You might have, so a neural network might be used, the output of which is the input parameters that are the ones that you should sweep for this particular problem. And this has great success in chip design in that it's, because there's so much data for these simulation runs that have been done over the years. So you can use that to train these models about which simulation runs are going to be more relevant to others. We don't have conclusive, I won't claim conclusive results about that, but that's in progress and it looks very promising. So that's ML-driven traditional simulation. Then what if we kind of go in between? So it's not a full surrogate where we're taking it all out, and it's not just sort of driven from the outside. But what if we go in the middle? What if we kind of combine both neural networks and traditional PDE models and try to run those and see what happens? An example here would be something where you have a particularly nasty, your model itself, even if it's an analytical model, has a particularly nasty, intractable, intractably, whatever, hard to compute, viscous term, for instance. You might just take out a single term, right? You have ANSYS Fluent is a computational fluid dynamics tool. They have a user-defined function capability inside the inner simulation loop. Well, I can use that to call out to evaluate a neural network. It's very, very cool, very promising. I'm probably most excited about the hybrid aspects of this, although the inverse problem is really there's just so much value, so much potential in these approaches. So to wrap up what I was talking about, we have surrogates, we have inverse problems, we have ML-driven HPC, and we have hybrid, new ways to apply AI. So I am very excited about scientific ML. I'm very excited about the future of scientific ML. I'm actually trying to create my next class instead, I'm working on creating a scientific machine learning one. It's more of an elective type of a class instead of a core data engineering sort of a class. But I asked for help in this, right? So this is something that's relatively new in the AI ML communities. And I ask you to start looking around at more practical problems that we can apply this to. And while of course, all of these things, applying AI to real life is very dangerous without those test frameworks, without the rails that we put around the problem itself. If we're flying a helicopter, don't let it do the option where to flip it over, right? That's just not I know that's a gross oversimplification, but the example, but it's still important to recognize the limitations of the models and the test frameworks that we're using to validate these models and have that feedback into the training parts of the MLOps pipelines as well. Okay, I think that's time. So there are some resources on this. I guess we'll share these. Thank you for your time, and I'll leave you with the dance part.
Mark, I think we got one question. Mike's going to ask it of you, so don't go anywhere.
Okay, I might stop sharing because I can't see the chat while I'm sharing.
It doesn't matter. Mike's got it under control.
I'll verbalize it, Mark. It's really the questions around, back on the observability topic. Yeah. Is that including detection of drift on the incoming features as well as drift on the model outputs as well itself?
Yes. Yeah. When I say observability in an ML context, I'm talking about a very general term there. What I mean there is adding the ability to add instrumentation into every step of your pipeline that absolutely includes what's happening on ingest. Now, you might not be able to detect drift without an actual model evaluated as part of that process. Right. And there are plenty of situations in which we do that. Maybe even on edge, you might have models that are trained and then pushed out to edge and evaluated solely to detect drift on inputs. Mm-hmm. Right. So absolutely. Yeah.
Yeah. Great. And my sense is we need to keep focusing on detecting bias as well. Because
oh my God, absolutely. Yes. And it's because the measurement process is inherently flawed. And at a very, very basic level, you can even bring this back to sort of like you can't know, even in physical phenomena, you can't know full information about a scenario. So you make choices about what you're looking at any given time, and that affects what you're looking at. So that also plays up to bias in surveys and in demographic data and things like this. It's always there. Your data sets are always flawed. It's very important. Like there's a similar spiel, if you will, about testing and characterizing the support of your models that I give my students that's involved with characterizing what's going on with your data sets and how bad they are and how you capture the metadata associated with potential flaws that you've identified in your data, because the flaws are always there. You need to capture them and you need to communicate them. Yep. Critically important.
Very good.